reservations in two-way slabs by means of yield lines. This video deals with the cases 31 to 35. It's about a slab on two sides simply supported and on the other two sides fixed end supports. This will handle case 33. It's a HB because it's on the side B. It's an HB square hole. We are first dealing with a yield pattern, which I call horizontal because there is one horizontal yield line. And this is where alpha, which is B over A, when alpha is bigger than 1.7, then you will have an horizontal yield line because we use the 60-30 degree rule for the position of the yield lines. It's a two-way slab. It means that B must be between A and 2A. Square reservation D1 is equal to D2. At the edge, D3 is 0. And it's moving between the two yield lines, between those two yield lines. It's not crossing the yield line. So the two limits are indicated here below. Of course, D1, the size of the reservation will be smaller than A over 2. To visualize it, then you have this or on the right-hand side or the left-hand side. And D4 is this distance from there to there, and that are the two limits, depending on the size B, of course. And this is the value of S1, S2, S3, and S4. Values of the S parameter. We can now calculate the work done by the external forces. And this is equal to, when we look at the rectangular sections, then we have A times this, which is B minus S1 minus S3. And we multiply by the mean deflection, which is delta over 2. We add to that the sections which are comprised of triangles. And this is A times S1 and A times S3. And the mean deflection is delta over 3. Now we have to subtract the reservation, and then it's d1 times d1. The maximum deflection here at that point is d1 delta times d1 over s4, and the mean deflection then is 1/2 of it. Then we can substitute the parameters, and then we got this simplified formula. The work done by the internal forces is equal to this yield line projected on this axis of rotation. It gives you B times the angle of rotation delta over S4. At the bottom we got B projected on this axis of rotation. So it's B divided by S2. And then we have on the side, we have A divided by S3. This is also A divided by S3. And this is A divided by S1. And we also have the A divided by S1, which gives you this expression. And we end up with this formulation. Now to find M, B is equal to E, and then we can calculate M, but we will do it with dimensionless parameters, which means alpha is B over A and alpha 1 is D1 over A. And then you have a nice formula for the maximum bending moment. In the case that alpha is bigger than square root of 3, then it will look like that. You will notice that this formula is independent of D4. So be careful because the condition on D4 must be fulfilled before you can apply this formula. Now we look at the other case for the vertical iteration of the yield lines. It means when alpha is smaller than 1.7, then you have this situation. two-way slab stays the same. The square reservation, the edge, so D3 is 0, and also the D4 is between those two yield lines, this and this yield line. Now you will see here how it will look. It will go like that with the values of S and the limit on D3. D3 is this distance. We can calculate now the work done by the external forces, which is, for instance, for the which is for the rectangular section, it is B times this piece, which is A minus S4 minus S2, and multiplied by delta over 2, which is the mean deflection. Then we got the triangle, the areas composed of triangles. So we got B times S4 and B times S2, and the mean deflection is delta over 3. Now we subtract the reservation, which is D1 times D1, and the maximum deflection on this side is D1 divided by S4, or delta D1 multiplied by S4, or divided by S4, sorry. So the mean deflection, it's a rectangle, is half of it. So it's D1 times D1 times D1 divided by S4 and half of it. Substituting for the values of S gives you this expression for E. We can now calculate the work done by the internal forces. We take this yield line, project it to this axis. So you got Bm times B times the angle of rotation, which is delta over S4. And for the other line here, it's B divided by 2. And then we got this yield line, it's A divided by S3. And we got here also A divided by S3. And then we got this yield line projected on this axis. It's A divided by S1. And this yield line is also A divided by S1. Substituting for the variables, we got this expression for D. To find M, we make D and E equal, and we use dimensionless parameters. Then we got this expression in the case of a vertical yield line pattern. It means when alpha is bigger than square root of 3, then you have this expression. Again, this is independent of the 4, which is this one. We can give an example. The case of a slab 8 by 13 meters, and we have reservation at 2 by 2 meters at a distance of 4 meters. The slab is 250 millimeters, concrete cover 40, the floor finish 2, and the mobile load 10 kilonewton per square meter. So what is the needed reinforcement in this slab? We check the boundaries, and D3 must be between those two boundaries. So we see that D1 2 meters and B 11 meters. So we see that D3 must be between 3.4 and 5.5. So it's 4. So it's okay. It's an edge B square hole base 33. Loads in ultimate limit state 1.35 times the permanent loads plus 1.5 times mobile loads gives you 26.14 kilonewton per square meter. These are the parameters of the example that we are looking for. Alpha is 11 over 8, which is 1.37, and 1.37 is smaller than the 1.7 of smaller than the square root of 3. So we are in the vertical system of yield lines. And alpha 1 is 2 meters divided by 8, it's 0.25. Now we can easily find the maximum bending moment. And it's 63.77 kilonewton meter per meter. We convert this bending moment into reinforcement. We calculate the lever arm. We calculate the mean lever arm, which is 189 millimeters. And the reinforcement is 1.1 times the maximum bending moment divided by the lever arm and divided by the yield strength of the reinforcement. It gives you 905 square millimeters per meter, or 8 diameters, 12 per meter will be all right. 905. So just take care, because we have positive and negative yield lines. So it is 8 diameters, 12 per meter with X and Y direction on top and bottom. So 4 times. Now we have a second example, an existing slab reinforced in 2 directions. We do not know what was the original load of the slab, and we do not know what is the amount of reinforcement in there. Now they want to make a reservation in this slab, 2.4 by 2.4, like is indicated here. It is possible. First, you calculate alpha. Alpha is 12 over 6, so it's 2. So it is still a two-way slab. And because alpha is 2, it's bigger than the 1.7 of square root of 3, so it's horizontal. So we are in the horizontal scheme of yield lines. We know that the maximum bending moment without a hole, without reservation, and we divide this maximum bending moment by the total load, because we do not know the load, so we want it out of our equations. Then m0 over q is then equal to this. And we can calculate that because we know what alpha is. So we have 2.029 from this quantity. And the maximum bending moment with the hole is then equal to 1.847 meter per meter. This means that the bearing capacity is 100 times m0 divided by m is 110. So making a reservation like this leads to no loss in bearing capacity. So you do not have to put more reinforcement in it, you can make this reservation. Bearing capacity is defined as 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. We work with dimensionless parameters. Then in formula, you have something like this. And the formula, you can only use this case 33 when the following conditions are fulfilled. Alpha must be between 1 and 2. Alpha 1 must be between those two limits. And alpha 3 must be between those two limits. In this case, we can use the set formula. We've seen in previous slides that m for the vertical pattern is this equation, and for the horizontal situation, it is this formula. So it means that when alpha is bigger than square root of 3, then you use the horizontal formula. If it's smaller, you use the vertical formula. Now we can put that into a graph. Alpha 1 is the size of the reservation going from 0 to 0.5 maximum. And on the y-axis, it's the bearing capacity. And you will see this is 100% and this is 115 and 95. And it's done for alpha equals 1, the red curve equals 1.5, the blue curve, and the black curve for alpha 2. So everything is between those two curves. Now we have the condition that alpha 1 must be between those two values, but this value depending on alpha. And alpha 4 must also be fulfilled. So now what we can do is, for instance, we take alpha is 1, then we see that alpha 1 must be smaller than 0.289. And this condition, when alpha is 1, and this is equal to that, otherwise you cannot have an alpha 4, then alpha 1 must be smaller than 0.224. See, this restriction is more severe than the other one. We do the same for alpha 1.5 and alpha 2, and then you will see each time that this condition supersedes this condition. The maximum value, for instance, for alpha equals 2, that is the black curve, then you will see here for the black curve, alpha 4, 0.45, for instance, I have here the dotted line, which is the bearing capacity calculated for alpha 1 equals 0.448. The red one is for alpha equals 1, and the bearing capacity there for alpha 1 equals 0.224 is 105. So this is the maximum limit. It means that for the uh, formula cannot be used for values higher than this because alpha 1 must be smaller than 0.224. It must be smaller than 0.24. So this portion of the line of the curve is not valid. So only this portion is valid. We do the same for alpha equals 1.5, and you see that the bearing capacity for this value, the limit value is 109, which is this line. So it means that the blue curve there, this is not valid. Only this portion counts. Then we do the same for the black curve, and it stops there at this intersection. Higher up, it's not valid anymore. This is all valid. So we can conclude that a square roll at the edge of a rectangular concrete slab type 33 has no loss in bearing capacity as long as the yield lines are not crossed. So this type of reservations do not influence the bearing capacity of the slab because they are just not crossing any yield lines.